much to him. Now we will be moving on to our last speaker for the day, which is our research student spotlight on Zayan Zamir. Let me just share my screen. So Zayan is a year 10 student at Sharjah English School, UAE. He is currently in the US, however, for a competition. So his speech will be pre-recorded. He is an aspiring electrical engineer, actually, rather than a doctor. However, he has interest in robotics, AI, and neurotechnology. As a competitor in international FIRST Robotics competitions, he develops intelligent systems addressing real-world challenges. So while his current focus for today's talk will be brain-computer interfaces, he also spends his time researching about neural decoding, neuroprosthetic technologies, and bridging the gap between human intent and machine action. He is presenting Decoding Thought, How AI is Transforming Brain-Computer Interfaces. Okay, the video will be playing shortly. Okay, I think everyone can see. I will play now.
Good morning, everyone. My name is Zayan Zamir, and I'm a Year 10 student from Sharjah English School, talking about how AI is transforming brain-computer interfaces. Now, when most people hear the term brain-computer interface, they immediately think of science fiction. But brain-computer interfaces, or BCIs, are already being used in the real world today. On the left, we see a person controlling a computer to play chess using neural activity. On the right, we see a robotic arm being controlled directly through brain signals. What makes these technologies remarkable is that they bypass traditional methods of interaction, such as keyboards, mice, or even physical movement. Instead, they create a direct communication pathway between the brain and an external device. For individuals living with paralysis or severe neurological conditions, this technology has the potential to restore communication, independence, and quality of life. But this raises an important question. How can a computer actually understand what a person is thinking? To answer that question, we first need to understand the challenge. Every movement, word, and intention originates from billions of neurons communicating through electrical signals. The problem is that these signals are incredibly small, often measured in microvolts, and they are buried beneath large amounts of biological and environmental noise. Eye blinks, muscle movements, electrical devices, and even natural variations in brain activity can interfere with the signals researchers are trying to capture. This creates what many researchers consider the biggest bottleneck in BCI development. How do we extract meaningful information from such noisy neural data? Before a computer can understand a thought, it must first find the signal hidden within noise. Researchers use different technologies to record neural activity. The most common is EEG, or electroencephalography, which records signals through electrodes placed on the scalp. EEG is non-invasive and relatively accessible, but it provides limited spatial resolution. More advanced approaches include electrocorticography, or ECOG, where electrodes are placed directly on the brain surface, producing higher quality signals. Some research systems go even further by using intracortical microelectrode arrays capable of recording activity from individual neurons. This creates an important trade-off. Generally, higher quality signals require more invasive procedures. As a result, researchers must constantly balance signal fidelity, safety, and practicality when designing brain-computer interfaces. Now, once neural signals have been recorded, the next challenge is interpretation. This is where artificial intelligence becomes essential. First, engineers use signal processing techniques to filter noise and isolate meaningful neural patterns. Then machine learning algorithms analyze those patterns and attempt to predict a user's intended action. This process is known as neural decoding. Early BCIs relied on simple rule-based systems. Modern systems increasingly use deep learning models capable of identifying complex relationships within neural activity. In many ways, AI acts as a translator between the language of neurons and the language of computers. And this is the true frontier of brain-computer interface research. Not simply recording brain activity, but accurately understanding what it means. Now, once intention has been decoded, it can be transformed into action. A modern BCI follows a pipeline. Neural activity is recorded, AI predicts the user's intention, and that prediction is converted into commands for an external device. These commands can move a cursor, control a robotic arm, generate speech, or operate assistive technologies. Now, one of the greatest challenges is latency. The entire process must happen almost instantly. Even small delays can make a system feel unnatural and difficult to use. The ultimate goal is seamless communication between the brain and technology. And one of the most exciting applications of neural decoding is speech restoration. Researchers are developing brain-computer interfaces capable of decoding intended speech directly from neural activity and converting it into text or synthesized voice. Instead of relying on the muscles involved with speaking, these systems interpret the neural patterns associated with speech production itself. For individuals who have lost the ability to communicate verbally, this technology could provide an entirely new way to interact with the world. And one recent example demonstrates just how powerful this approach can be. Kenneth over here was diagnosed with ALS, a neurodegenerative disease that gradually damages communication between the brain and the muscles. It's usually described as something like a severed internet cable. As his condition progressed, speaking became increasingly difficult and exhausting. Researchers implanted a brain-computer interface designed to record neural activity related to speech. Using machine learning, the system learned to associate Kenneth's neural patterns with the words he intended to say. Instead of relying on damaged muscles, the BCI bypassed the pathway entirely and decoded speech directly from neural intent. For the first time, Kenneth was able to communicate using a digital recreation of his own voice. This shows that brain-computer interfaces are not simply controlling machines. They're restoring one of the most fundamental aspects of being human, the ability to communicate. Now, looking ahead, researchers are developing increasingly adaptive AI systems that can learn from individual users and improve over time. Now, future BCIs may enable real-time speech generation, artificial sensory feedback, and more natural interaction between humans and technology. The future of BCIs is not reading thoughts, it is understanding intention. And by combining neuroscience, artificial intelligence, and engineering, we are moving closer to a world where neural activity can be transformed directly into meaningful action. Thank you so much for listening.
Thank you so much to Zayan for that fascinating presentation and for giving us a glimpse into the future of artificial intelligence and BCIs. I will now share my screen for our finale.